G'day grade 10s, welcome to video 5 for your year 10 chemistry unit. And you might be going, what happened to video 4? Just to keep all the numbers aligned the same way that it's presented on eLearn. Video 4 will come in relation to solubility later on in the unit after we've completed the assessment. It used to be done beforehand, but by rearranging the schedule we got it done a little bit later so that the activity can go with that and not be crammed into the middle. So let's get into talking about reaction rates. So here's our Walt. We're going to learn a couple of things here. Well, firstly, what are the variables that affect reaction rate? And secondly, we're going to look at how we can measure and analyze reaction rate, and that's going to be really important. So things I need you to be able to do, you should be able to use correct scientific vocab, identify and apply the 5 ways to increase rate of chemical reaction, and then explain those, and then use graphical data to compare and calculate your reaction rates. 2 reasons. If you go into industrial chemistry, reaction rates are pretty important. The other thing, this is part of the assignment now. I know in 2020 we're not doing the assignment, however we'll be doing it in class as a learning activity, and some of the graphical skills that we're going to use here will be good for your physics in term 3. So on we go. So here is a pondering question for you. You have several moth. You have several large pieces of wood in a fire. What are a couple of ways you can increase the rate of burning? Okay, so how could we make it burn faster? Give it a moment. Okay. So a couple of things you could do. You could change the size of the pieces, add some small pieces instead of big pieces, or break those big pieces up. You could fan it up or blow onto it to add more oxygen. Some of you might have said you could throw some fuel on it, but regardless of what we're doing here, the goal is to increase the reaction rate. So the first one, by making the pieces smaller, we're increasing the surface area. Okay, and we'll get to why that's important in a second. Fire requires oxygen. Yes, it's burning the wood or might be burning fuel, but the other reagent for it is oxygen. And so if we add more oxygen, then we'll get a better reaction. In terms of adding petrol to it, that would be considered like a catalyst effect, where we add petrol to something and we can cause it to increase its rate of burning. Obviously petrol won't work for all reactions, but it will work really well for combustion reactions. Okay, so here's a few terminology words. Match them up. Shouldn't take you too long. Okay, I'll identify a couple of things. The word rate is going to be really important here. Number 4, that matches up to A. Okay, so a rate is always something where we measure one thing and we compare it to another thing by dividing it. Okay. For example, if you go to the petrol station, you're buying petrol for this many dollars per litre. You're comparing dollars with litres. If you go down the speed limit, you're going maybe at 60 kilometres per hour. Kilometres compared to hours. And gradient is another one that's going to be important there, and you might sort of clue in about those. Now, concentration's sort of a newish one there as well. At least not newish, but you might not have seen it lately, so let's refresh our memory. Concentration, the number of particles per unit volume. Okay, if we have the same particles in a big volume compared to the same particles in a small volume, concentration is different. If I take the class and I push it into the storage room in the chemistry lab, you're going to be very concentrated, you're going to be very close together. If I go and let you out into the Great Hall, well, you're going to be able to spread out, so you're not that concentrated. So our definition, remember, for a reaction is it occurs when a reactant, okay, or reactants, changes into a product or products, depending on what type of reaction it is. So that's where something changes into something else. And for that to happen, that means either the amount of stuff we start with, the amount of reactants we start with, must be getting less over time. Not the total atoms will be getting less, because remember, reaction is just rearranging of atoms, but the atoms arranged into that form, okay, in the presence of those reactants, is getting less. If you have some sugar, okay, and you set it on fire, the amount of sugar will get less, okay? The amount of oxygen nearby will get less, but then the products will increase. Oops, sorry, just too far. The product will increase over time. Okay. Now both of these are true. Reactants goes down, products goes up, and so that means whenever you're doing an experiment to look at reaction rates, you should think, what's easiest for you to do? Is it easier for me to measure the how much I started with and what's left over, or is it easier to measure how much is being made? It depends on what you're working with. So our rate of reaction is the speed at which something is used up, or the speed at which something is produced. And we have a fairly standard graph here of what this could look like. You can see across the x-axis time, and up the right hand side here we have NO2, nitrous oxide, concentration. So this could be measured in grams, kilograms, moles, which is a unit that we'll deal with later on a little bit later on in the year, but we'll especially deal with it in year 11 and 12 chemistry. But just something that we can use to measure how much there is. Okay, you might notice the shape of the graph, it's curving off. That'll be pretty important as well. So if we take a look at that graph, how did the rate change over time? So you have to ask yourself, how could you identify the rate from this graph, and then tell me what's happening to the rate. So give you a second to look at that. Okay, so the change in the gradient, also we can tell that the gradient is changing, okay, and it's getting less and less. And I will draw a few gradients on here. Hopefully my pen wants to behave a little bit more. So here is gradient here, while here is the gradient here, and here is the gradient here. And you can see over time it is getting less and less steep. Okay, though that last one's kind of a wonky tangent. Okay, so this tells us if the gradient matches to the reaction rate, that the reaction rate must be getting less over time, or the reaction is slowing down over time. And that's a fairly important thing to connect when you're doing these, because oops, that didn't actually change it. Because it will go down over time. So what you're going to do is, part of your analysis is you have to choose what section of your data you are going to analyze. Do you analyze the first 30 seconds? Do you analyze the whole thing? Do you analyze a period of time halfway through the middle of it? You're going to have to choose that and argue that. The rate of reaction over a very small time, okay, will give a instantaneous rate of reaction at that time. Okay, and what I mean by this is rates of reaction are not going to be constant, not at all. Okay? If at the start it's going at 10, or let's see, that was going at about roughly 1 times 10 to the negative 4 moles per litre per second. Oh, sorry, per 10 seconds, so 0.1. But then over a bit of time, it was taking a lot longer. So from 2 to 3 is, what's that? A bit over 20 and a bit seconds. Well, from 0 to 1 was less than, a bit less than 10 seconds there. Okay, so the rate of reaction changes, and you will have to calculate this. So how do we increase it, and how do we, how do we use these things to benefit ourselves? So oxygen and glucose, it's going on all the time in your body, okay, producing millions of ATPs every day. I think if I watched a video the other day, I think the amount of ATP you would have to use for yourself in one day is pretty close to your body mass in terms of how much we keep making. very large amount. But if I go and put some sugar out on the table, why doesn't it just react with the oxygen around it? And how do we speed these things up? So we need to firstly talk about why something will have a reaction or it doesn't. For two things to react, there need to be two things. One, enough energy. Okay, basically, they need to be going fast enough. And it needs to be in the right orientation. And I'll show you what orientation means on the next slide. The more reactions or fruitful reactions that we have, the greater the reaction rate. Okay? So here we have two examples. Our two compounds collide, two molecules collide. Here it produces something, here it doesn't, because there just wasn't enough energy to break those bonds and let them reform. Here again, same thing, drawn a different way. Here is an example of poor orientation. So you see here A and B are colliding, but the other A's and B's are not touching, and so they will not form this intermediate before breaking up into their new products. So you have to have those two things. It has to be going fast enough. Normally we would use arrow size to represent how fast something is going. See here, this arrow is smaller than this arrow, so the energy here that they have is not as high as the energy here. But this one produced it because it was in the right orientation. Even though this one was faster, it still didn't make anything because it was not in the right orientation. Okay? Alright, now, there are 5 things that we can use to speed up a reaction. Now, there's a video called Collision Theory on my OneDrive. You can also find it on TED-Ed. It's a great animated video about chemistry and reaction rates. Well worth looking over there as well if you're not watching this from an EQ site. But have a look at those videos, and there are 5 things I've given you there that have an analogy in terms of chemistry. So I'll give you a second. Okay, hopefully you've paused, gone and have a watch that video, because I'm not actually going to fill this table in. Sorry, so definitely go have a look at that. But we're going to ask some questions about it when my thing wants to skip to the next page. So, in our video analogy, adding more students is analogous to doing what? Well, we've got decreasing the volume, adding more particles, adding a catalyst, or increasing the temperature. The correct answer is adding more particles. Okay, so if we add more particles to an experiment, if we increase the concentration, we should get a faster reaction rate. And if you think about it, it makes sense, because it means you've got more stuff in there, there's going to be more collisions happening, and the chances are more of them will be the right orientation, the right speed. Whoops, sorry, I went too far there. The pen is just being really silly. Okay, shrinking the hallways, same 4 options, so obviously can't be B. Yeah, well, shrinking the hallways is going to be about decreasing the volume of the reaction container. Now, that one is actually quite tricky for us to do, because if you think about having solids or liquids, and generally we're going to deal with liquids here, the shape of the container is not going to significantly affect it unless you went from something being very wide and flat to being circular, and even then you'd get maybe a small change. Statistically, it's not going to be a big difference when you're dealing with such microscopic things. This one about volume mostly deals with gases, and that's because when you decrease the volume of a gas, you increase the pressure, because you're basically increasing the concentration. You're bringing it closer together. Okay? So in terms of this, A, or decreasing the volume, is really more about gases, while adding more particles works quite well for liquids. The other two will be usable for both. Okay, shortening the time between periods, the time between classes. I know we don't really have that at Glenalla, but for example, the idea would be if instead of 5 minutes from the first bell to second bell coming out of lunches, we gave you 2 minutes, and then if you didn't get there in 2 minutes, you got an automatic weekend detention on a Saturday. So you'd be panicking and trying to get there pretty quick. Okay, well that's about the temperature increasing the speed of our particles. And so, as we said, they've got to collide with enough energy. So if they go faster and faster, they should have enough energy. And our last one here, hiring a matchmaker. Well, that's a chemical catalyst. As you saw in the diagram, the catalyst basically, also in the video, basically brings two atoms together into the right orientation, or two compounds together in the right orientation, so that it's easier for the reaction to occur. Our body has a lot of these. They're called enzymes. Now, there was one last one that was not mentioned on there. Let's see. And that would be increasing the surface area, which I believe the analogy in the experiment was about breaking up, in the video was about breaking up the groups of kids. Okay, and that's an easy one to do, especially solids, because if you turn a solid from being a tablet, for example, into a powder, well, the smaller the pieces, the bigger the surface area, the easier the reaction will go. Okay, so what are the two conditions that have to occur? Well, hopefully you can see there it has to be answer D, so that's both A and B. Okay. So let's talk about activation energy. Last year we talked about endothermic and exothermic reactions in Year 9 chemistry. So an activation energy is the minimum energy needed to get over this hill here. So if this is what they rush together, they've got to have enough energy to get to here, so they need to get over that, so then they can fall back down. And sometimes this will help determine if something is an endothermic or an exothermic reaction. Endothermic ones obviously get colder, you might remember that from last year, and so they won't give energy into the system to keep the reaction going. This one here is exothermic though. Once it gets over, well, it releases a bunch of energy, and that energy there can go to getting the next reaction along. Obviously it won't do self-sustaining, it wouldn't be a heap of energy to get the next one going. However, it would help quite a bit. And here's an example. If I want that sugar to start reacting with oxygen, I need to give it a bit of fire, I need to give it a bit of extra activation energy, and then it continues on from there. So temperature. Let's talk about our three things that you can really change for experiment. Now, one of these three things will be asked about on your exam, and we're going to do one of those three things in class as well. So, temperature, measure the average kinetic energy in a substance. And you're told here that the longer arrows means it's got a higher average speed. Remember, speed and kinetic energy go hand in hand. Think back to grade 8. So which one of these two has the higher kinetic energy? Well, it'll be the one on the right, because it's got longer arrows. Longer arrows means more speed, and more speed means more kinetic energy. So this means that this one has the higher temperature. Okay, the particles are moving faster, and so they feel hotter. Our second big factor that we can choose for the experiment is the area of the outer surface, okay, the surface area. These two cubes here, they've got the same mass, they've got the same volume, okay, though this one on the right's just sort of broken up a little bit. But the one on the right has a lot more surface area, and that's because we've cut down all three axes, and it's created all these new surfaces on the inside that weren't there. Okay. Which is what I just said. And so we see a pattern here. As we make the pieces smaller, even though the mass and the volume is still the same, the surface area gets bigger and bigger. So here the one cube is 16 centimeters cubed. Here we've got 8 cubes of 2 centimeters squared. Sorry, 2 centimeters cubed. And here we have 64 of 0.25 centimeters cubed each. So a good understanding there that if you have some object and you keep breaking it up into smaller and smaller pieces, as volume gets smaller, surface area will increase, and so therefore so should the reaction rate. Our last thing is concentration. Now, concentration, a nice easy way for you to visualize it is imagine making some cordial at home. If you just pour lots of cordial but not much water, you kind of get what's over here on the right. If you put a little bit of cordial but lots of water, you get what's over here on the left. There is a special couple of language, so anything that's dissolved is called the solute, while the stuff that is dissolved in is called the solvent. Most of the time, 99% of the time, that's water, at least especially at this level. So if we had things like hydrochloric acid, well, that would be the solute, while the water it's in would be the solvent. If we had liquid sodium hydrogen carbonate, then that would be the solute, and then the water that it's in would be the solvent. This is all the definition of concentration is. And here we can see, well, I have the same number of particles. You can count them. There's 6 on the left and 6 on the right. However, if we add some water, if we dilute it, okay, then the one on the left is now a lot more concentrated than the one on the right. Okay? Even though it's the same amount of stuff, the concentration of the stuff is now a lot less. And so think about it. If I was to add something to react with these 6 particles, because these 6 particles have so much more room to spread out, oops, my pen is just being silly. Because this has so much more room to spread out, it's going to take longer for the particles to find the compounds to find each other and have a viable reaction. Here, they're a lot closer to each other, so it's easier to find. So as concentration goes up, reaction rate should go up as well. Alright, well, as you just clued in, this is the end of our video for reaction rates. Definitely have a relook at the metal reactivity video, because you're going to need to get information out of that in order to calculate some reaction rates to practice for your assignment and for your exam. Have a great night, guys. Talk to you soon. Bye.